is Aviv, and I'm coming from LSEC at the Hebrew University here. And I want to start and say thank you to the Institute and to Mario and Miri for hosting us and allowing us to have this conference. I also want to say thank you for the guests, the international guests who came to Israel this time during the war, and pray with you that it will end and the hostility will end and the kidnapper and the people who were kidnapped will be released. And also want to thank the audience, the Israeli audience, because I know it's a complicated day, and many of you might want to be in a protest. So I'm really thankful for you to coming this day. I know that the university said that there will be a strike if the situation will continue, and I really support that. And let's hope that things will change in Israel. And with that, I will move to iron and mapping of iron and trying to map the homeostasis of iron. And I need to get used to this. Okay, so we already heard the importance of the homeostasis of iron in the brain and in tissue. I mean, how do you make it more?
זה מדי פעם כאילו מאבד את הקישוריות.
It's just a long delay.
Very long.
There it is, yeah, it's appeared.
מה שאני עושה זה אני מזיז שנייה. או שזה הבטח.
אתה צריך ללחוץ, לא להזיז.
Okay. And so we heard about the importance of the homeostasis of iron in the brain, and as we already heard, iron is mostly aggregate in ferritin in the tissue, but it also have a mobilized component, and much of it is inside transfer in the tissue. And all this homeostasis is critical for multiple neurodegenerative diseases and in cancer. In the brain, also out of the brain, it has a critical effect, as we heard. Typically, in MRI, it's really hard to measure this aspect of homeostasis. But if we look on different iron forms and iron environment, at least ex vivo or in vitro, we can actually know that there is an effect of the different environment in which iron is held on the MRI measurement. And this is a work of Rona that is sitting here. And she here used different type of iron environments. So it's proteins which have iron inside them, either in the environment of lipids or proteins. And you can see here the different concentration. These are the different dots. And in the y-axis, we see here R2 star, which is a common measurement for that's known to be sensitive to iron. And you can see that different compound or different environment have different what we call relaxivity. This is the slope that changes as function of concentration. We can also show that if we would also look on the iron concentration, not the protein concentration. So we can summarize that as the iron relaxivity of R2 star, and different component or different environment will have a different relaxivity. And this is known. This is just a replication of a known result that done many years ago, several times, and this is a replication in vitro in our lab. And so what I'm going to show today in the first part of the talk is kind of summary of a work of Shir Filu, who was a PhD student in our lab, wonderful PhD student, now working with Evgenia. And she developed this circle in which she first proposed a biophysical model, a very simple model. We then check it in vitro with the work of Rona using phantoms, and then we'll see the application in vivo and comparison to ex vivo. And actually, I think, what is going on in here? I actually missed a slide, which is this. And I want to say that, I wanted to start with this one to say that we actually know that R2 star is a very good measurement of iron, and this is just a replication of work of others. Here is R2 star measure in vivo in a group of subjects across multiple brain regions. That's the colors. There are younger subjects here and older subjects here. And the x-axis is measurement done in a different cohort. So it's aggregation of data from different works. and this is the level of iron versus the outer star. And that's kind of like echoing thing that was said here before. Outer star is very sensitive to the level of iron in the brain, at least in this kind of view. It looks like almost a linear relationship between iron level and outer star measurement. Okay, so now I'm going to continue and go back to this. Okay, so now the model is as follows. Not only outer star that is sensitive to iron, there's other relaxation mechanisms that are sensitive to iron, sensitive in a different way, and probably in a different mechanism, maybe also with a different relaxivity. So that was the thought of Shear, and she said, let's also add R1, another very common quantitative measurement that's supposed to be also sensitive to iron, and see what happens. And the idea is to combine those two quantitative measurements. And the thought behind it is that, and actually Evgenia kind of helped me think it through, is that when we look on outer star, we think that the effect is kind of mesoscopic effect, kind of similar to what Karin said about QSM. So the effect is kind of larger in space. And the case of R1, the effect is much more local. So there is a need of interaction between the water molecule, the hydrogen in the water molecule, and the iron component in order to create effect on the relaxation of R1. So we have very different mechanism that affecting the signal in MRI. And that could be useful. So here is if we take the same sample that I showed you before we saw the R2 star and the different relaxivity of the different environment, and this is the same samples now with R1, they also have a linear dependency on the concentration of these environments, but the slope are different, the effects are different. Different environments create different effect on different relaxation mechanisms. So in general, we have the R2 star iron relaxivity and the R1 iron relaxivity, and they are different. Again, this is actually a replication of work that was published at least 20 or 30 years ago. So it's not, we just replicate something that was kind of new, known, and we replicate it here in a controlled way. Okay. So what we have here is we have a measurement of iron concentration that can change, and it's affecting the relaxation, and you have linear relationship between them. And the problem is that in vivo we just don't know the iron concentration, so we cannot really get this relaxivity parameter, which seems interesting because it will be sensitive to the iron environment. So what she was proposing let's take the measurement themselves. Those we can measure in vivo, and look on their linear relationship one on the other. Maybe that will be a way to assess this relaxivity phenomena. And the prediction that they also will be linear one to the other, and the slope of this thing, we call it the R1 to R2 star relaxivity, will be the ratio of these relaxivities that can be measured only in vitro or ex vivo. This one can be measured in vivo. That's the prediction. In this very simple case, right? So first we can check it. So that's exactly what I was doing. And here we see the same sample now R1 against R2 star for different environment, different iron environments. And we can see that they have different slope. So in theory, this R1 to R2 star relaxivity seem to be sensitive to the iron environment, not the concentration, but the iron environment itself. And we also have a prediction that it will be the ratio of the relaxivity that we measured before, and it does. It's not one-to-one, but it's very similar. So this prediction works here in the phantoms. Okay. So now we can try to do that in vivo. And in vivo, so we want to measure relaxivity in vivo, but how would we do that? We have a problem here. And the problem is as follows. Actually, in each voxel in the brain, we have one R1 measurement and one R2 star measurement. So I cannot really fit a line here. So I'm done. And so the solution that she came with is we're going to sacrifice resolution, essentially. And we're going to use an ROI-based approach. So now we have many voxels, and hopefully there will be a linear relationship also in the ROI. And then we're going to get some kind of relaxivity of the ROI. Okay, so we're going to have many voxel. So here we see a 2D histogram along one ROI, which is the thalamus in this case. And now what we can do is we first bin these values. Actually, binning is very important because there's a lot of variability which is not related to iron. And in some way, this kind of shrink this effect. And we're getting this, we can then depict the linear relationship between the two quantitative measurements, fit a line, and have the relaxivity measurement for this, at least the R1 to R2 star relationship for this ROI. That's what we quantify. So here we see single subject, 4 ROI, white matter, thalamus, putamen, and cortex. Each has its own linear relationship or close to linear relationship, and we can fit the relaxivity. And we can do it also across many subjects. Here we see a case of 21 subjects, and across many ROIs, as before, color represent ROI. And here they organize according to their relaxivity value. And you can see here that the variability within subject, between subject is smaller than the variability between ROIs. So it's actually a signature of the ROIs. And an interesting phenomenon is it's actually it's not the same as looking on the R1 or the R2 star. That's actually key. So it's not just the same measurement. Looking on this relaxivity give us additional information that exists in here. Also, if we look on the histogram, it's a typical histogram of R1 and R2 star when you have a peak of white matter and gray matter, and maybe subcortex somewhere in the middle. Actually, the histogram of this R1 to R2 star slope is different. So again, going with the idea that it captures some additional information that was kind of, well, it was always there, but was hidden and when we look on each quantitative measurement by itself. Okay, so now we can try to relate this quantitative value to ex vivo value and see if it actually represents anything that is related to the histology that we're interested at. So before, I kind of already showed you this figure, right? R2 star is highly correlated to iron concentration as measured by others, all measurement by others. So it's a different data set. This is in vivo, these are in vivo. This is the measurement as we find in aggregating data from histology. And what we find for the slope is that it doesn't go so much with the iron concentration, but it goes with another quantitative histological value that is measured, which is iron mobilization, which is typically in this work was quantified as the ratio of transferrin to total iron in the tissue. So it seems again that this kind of relaxivity measurement is sensitive to another aspect of the tissue besides just iron concentration. Okay, so that was across data set and across regions. We also want to do it on a single subject level and with the same subject. The problem is that you have to sacrifice the subject, right, to actually look inside them. So we actually collaborate with a neurosurgeon. We didn't sacrifice anyone. But we look on people which have a meningioma. And with people with meningioma, they typically have, before surgery, they're going to have a surgery. But before surgery, there is imaging procedure. So we essentially just make sure that they actually have a quantitative measurement and not just a clinical measurement when they do the scan before surgery. So that's the work with Tal Shachar that back then was in Shaarei Tzedek Medical Center. Then there is a surgical intervention. Maybe it will work, yeah. And after that, we actually keep some of the tissue. Most of it, they throw it away, so we just don't throw it. And we evaluate the ratio of transferrin to ferritin using Western blot. That was one of the things we did. The other thing was looking on gene expression. I will show you both, what we see when we do that. But before I'm doing that, I just want to highlight one more interesting point is that the tumor, by the way, have a very different characteristic, slope, when you look on R1 to R2 star versus the tissue nearby, the gray matter and the white matter. So there's something about the tumor that is very different than the tissue that they are surrounding. Actually, the effect is very big. It's as big as the effect of a gadolinium enhancement. So typically, when we want to see this tumor, we actually enhance the contrast by gadolinium. And the effect here is, well, the statistical effect here between the tumor and the tissue around it is similar in terms of statistical difference as we measure in here, although the resolution here is poor, right? So that's not a clear translation from one to the other. But in terms of the effect, it's a very strong effect. And this effect doesn't exist in just if you will look on R1 or R2 star, then we don't see this big difference between the tumor and the tissue around it, gray matter or white matter. Okay, so now let's look actually in the thing we actually want to discuss, if it moves. Here it is. So the homeostasis of iron. So we quantified transferrin to ferritin ratio within the tumors, within the subject, and compare it to the R1 to R2 star relaxivity within the tumor. We separate our group to two groups. Some of them have a high iron mobilization, and the other one have low. That's the level of separation we could get with the Western blot analysis, which is noisy by itself. And that's actually separate nicely in terms of R1 to R2 star relaxivity. So that's kind of another validation way of this measurement now within a subject, within the same group, which again we couldn't get if we would look on the quantitative measurement themselves, the R1 or the R2 star themselves. Okay. One last bit about this work is that we also collaborate with Nomi Habib from ELSEC, which she's famous for doing a gene expression. In this case, we did a bulk gene expression, and we kind of try to find families of genes that are kind of varies with our contrast, with the three contrasts that we have measured here. And we found about 101 set of genes that were related to the contrast that we measure in those tumors. And it was interesting to see that if we cluster them, I will do two in one. So if we cluster them, the R1 to R2 star slope is actually clustered separately from the original quantitative measurement. And there are many family of genes here which actually relate to iron mobilization that are kind of pulled in here. So that's an interesting, another interesting observation with this quantifier. And with that, I kind of can summarize this part in which, using in vitro measurement, we show that R1 to R2 star relaxivity is different for different iron form, different iron environment. It can be done in vivo, and it seems to vary across brain regions according to what we expect from histology, and also when we did the measurement within a tissue in the case of the tumors. And we believe that's a way to enhance the specificity or the molecular specificity to iron with MRI. So that's the thought. And when I met Amit actually in one of the demonstration actually, we said, oh, interesting, you're working on the same thing. Maybe we should do something together. And that's how we kind of started this project that Amit described before. And until we have the data with Amit, I will share with you a little bit of the work we're doing on Parkinson's disease. That's another thing that we are very interesting to research in the lab. And I try to relate what I just showed you to our data about Parkinson. And so in Parkinson, this is a project that Elior Drori, sitting here, kind of developed in the lab. And in collaboration with Professor Gilad Yalom from Shaarei Tzedek Medical Center, we recruit about almost 63 patients which have Parkinsonian patient and healthy control. You have here the statistics. And we took multiple quantitative measurement on this subject, and we tried to ask if we can find any signature for Parkinson. Before I say something about the main project we did, I will describe first a replication of the work I just showed you that Mariana did, and the poster is there if you want to see afterwards. I talked with Mariana. She essentially, it's a new data set. Here we have a young subject, older subject, and PD subject. So there's also additional population in this data set. And we again compare the x-axis the same as before, the one that came from histology, from work of others, and the the y-axis here are the different quantitative measurements that we got here, now on these 3 different group subjects. And we find that, again, R2 star in our quantitative measurement is the one that mostly related to the iron content, and R1 to R2 star relaxivity is the most related to the iron mobilization. That's what we find here, and this is a replication of the work I showed you before. But one thing to actually notice, and that while we have this replication of the agreement between the histology and the in vivo measurement, looking on this data, we don't see, per RI, we don't see a great separation between patient and control in terms of PD. I know there is mixed result. In our hand, there is no clear signature of iron for Parkinson. So we don't find it. It's not clear.
In those parameters.
Using these parameters. Also, we also try QSM, but so in those parameters we don't find it. And I will say a little bit about it, but before, what we try to do is to maybe to be more specialized and try to see maybe if we will be more specialized in space or in a subgroup, we might find it. And I will show you 2 attempts in this direction. One is the work of Elior, who developed this tool to identify striatal gradient. So the idea is as follow. In each subject, we identify a reading that we're interested at, and this was done mostly for the striatum. Here we see the example of the putamen. We find the putamen. We're running SVD analysis along it, identify the main axis of this object. And then when we have it, we can separate to different bins. And because we have quantitative measurement, we can actually sample the quantitative measurement in space and see if there is a variability in space in the measurement. Here you see an example of a single subject in R1 values. And it's nice, and you can see a nice separation in space of this value. And it's actually a measurement that is highly that you can replicate many times in many data sets that we try to do this measurement. So we find this gradient in space. And Elior took this tool, and with this new data set, he tried to see if he can find separation between patient and control. And in all these different quantitative measurements, we do find a gradient in all of them, including R2 star here. And these 2 also show interaction between position and group to say that there is a indication of separation. It's essentially a marker of separation between PD and healthy control in these two measurements. The major effect is actually in water fraction, so the fraction of tissue essentially to some kind of a measure of atrophy. But we also have such interaction also for R2 star. We don't find it in the relaxivity. Okay, so this is that. And then we also try to focus on the substantia nigra. That's the work of Mariana, which is here. And we try to ask ourselves, do we find a difference between healthy control and patient? We don't. As you can see here, the variability in the PD is very big in our data set, and we don't find a difference in here in terms of R2 star. But when we separate our group to different genetic mutation, and in Israel there are several, it's actually relatively easy to find a mutation which essentially known to have a different disease root. So the GBA mutation is one mutation that is very common in Ashkenazi Jews. The LAG mutation is another. This one considered to be an easier case of Parkinson, while this one considered a very hard case of Parkinson. And here, at least, we find this trend of relation between the R2 star and the different subgroup here, including the healthy control that you can see are here in the middle. But in terms of significance, this is not significant when we did enough checking, because we checked too many things. So if this test is by itself, it is, but we did so many things, too many tests to actually describe it as significant. And you can see also the group kind of becomes smaller as we subdivide our group. Anyway, we also look on the healthy control, and you can see that the control which have GBA also shows separation from people who have a GBA PD. So that's our hint. That was true both for R2 star and for the relaxivity, and those are hints that it might be that looking on different subgroup of a PD patient will allow us to better characterize the effect of iron and iron mobilization, and maybe also the change of the disease as it progresses with MRI, and to actually validate what I just said in the last two slides. We're actually now starting collaboration with Sourasky Medical Center. They have a big cohort of patients and MRI and genetic measurement. They just transfer the data, and soon Mariana will answer us, so we would know if it's actually if this prediction that come from the data will actually generalize to another data set. And I guess with that, I'm going to end just at this last line that in Parkinson's disease, we observed maybe a moderate change with iron that was either localized in space, it was in the posterior putamen, and maybe localized to a specific mutation. Both these things need to be validated. But still, I think that this idea of separating the iron content and the iron environment is actually valuable and could be interesting for many work that we heard about today. About to be done. This is just say thank you now. So I want to say thank you first to Shir. I mostly show her work, to Elior, to Mariana, to our clinical collaborator, Tal, and Nomi, Gilad, David, and the group in Sourasky Medical Center, the funding agency, and thank you.